My name's Rachel. I'm a master's student finishing this semester. So this is the project that I've been working on the past 2 years, Solar Synergies, and it's merging energy production with agricultural practices and habitat conservation. So a little bit of background, as we all know, the population of the world keeps increasing and is projected to increase to 9.7 billion people by 2050 per the United Nations. And so with that comes energy and agricultural needs. And so fossil fuels have been less, renewable energy has been increasing in popularity more compared to fossil fuels. And so 25% of the world's energy is predicted to come from solar power by 2050. And along with that, agricultural production will need to increase by 60% to meet food demands by 2050 for the population. So with the increase in renewable energy and agricultural practices comes a competition for land use. And so in order to mitigate this conflict, we have agrivoltaics. And so agrivoltaics is the co-location of photovoltaic power, PV power, with agricultural or natural habitats. And so agrivoltaics recently has been found to increase land productivity by 60 to 70%, which is huge to mitigate the conflicts. And so some benefits of agrivoltaics, as found in research, is an increase in ecosystem services. And so this could be through increase in crop yields through pollination, a reduction in soil erosion from shading from the panels, an increase in soil moisture and plant water use efficiency through shading as well, and then more efficient PV panels through a cooler microclimate from the panels. And then there are some downsides to agrivoltaics as well. And so that's a decrease in plant productivity, which depends on the species that you use, because as we know, not all species are shade tolerant. And then there are also a lot of establishment challenges. So when building solar farms, there's a lot of compaction with the soil that happens. And so that could be challenging for establishing vegetation cover. And then there could also be a decrease in electricity outputs from the dust in harvesting crops that can go on the panels. So our project, the main objective is to investigate the establishment of flowering, annual and perennial wildflowers and common forage species in solar farms in Florida to enhance pollinator habitats. And so with this, we looked at 4 different treatments. The first one being the hay grass, which was our control. The second being summer and winter annual cover crop mixes. The summer mix consisted of ashnominy, partridge pea, buckwheat, and crabgrass. And then the winter mix consisted of brassicas such as turnip, rapeseed, and then we had crimson clover, fall clover, and blue lupin. And then our third treatment, we had a native wildflower mix, which consisted of Phlox mundi, 2 Coreopsis species, bee balm, and black-eyed Susan. And then our fourth treatment was a dense perennial ground cover mix, which had rhizoma peanut, mimosa, and centipede grass. So our experimental design, just a basic overview of it, was that we had 2 locations. The first one, it was at a solar farm in Tallahassee operated by Origis Energy. And then our second location, we built mock solar panels in Gainesville at the UF IFAS Beef Research Unit, the BRU. And the mock solar panels were built to scale as the solar panels in Tallahassee. So same size, same measurements. And then we had 2 shade levels. Our first level was no shade, and then our second level was shade. So at Tallahassee, we could not plant in between the solar panels. And so we planted outside of the panels. So we had 4 blocks outside of the panels, no shade. And then we had shaded panels at the BRU because we planted in between the panels and outside of the panels. And then this was operated on a randomized complete block design, and our response variables were cover frequency, cover percentage, flower frequency, flower density, weed percentage, biomass, and then pollinator stuff, which Wilhelm will talk about. So some of the results, this is cover frequency, and let me orient you guys. So on our x-axis, we have the dates. And so we did this over 2 years. So the first year is on the left side, second year on the right side. On our y-axis, we have our response variable. And so the frequency is shown as a proportion, but could also be a percentage. So 1 equaling 100%, 0 equaling 0%. And then on the right side, we have the location and shade level. And then each panel for each location and shade level. So to go over this, for the cover frequency at the beef research unit, no shade level, our cover crop mix, which was treatment 2, overall performed higher than the other treatments. But as we can see, the wildflower mix in the second year increased towards the end of the season. And then similar trend with the shaded plots at the BRU, we had overall high target cover percentage by the cover crop mix, so treatment 2, and with the wildflower mix increasing towards the end of the second year. And with the Bahia grass and the low maintenance mix, our treatments 1 and treatment 4, they were consistently lower than the other 2 treatments. And then for Tallahassee, the no shade plots, kind of a mix of everything, but the Bahia grass performs pretty consistently throughout and higher than the other treatments. And so the previous vegetation cover at the solar farm was Bahia grass. And so we did land preparations, but obviously there could still be some Bahia grass that was there. So that's the cover frequency. And then for floral frequency, we had the cover crop mix performed consistently higher than treatments 1 and treatment 4, Bahia grass and low maintenance mix. And then we can see that the wildflower mix, the green, got higher in floral frequency as the second year went on towards the end of the season, and was also higher than the other treatments for all three locations and shade levels. But with Tallahassee, the Bahia grass performed higher than the others besides the wildflower mix. And then lastly, I'm going to show you guys the weed percentages. And so the weed percentages for the cover crop mix were lowest throughout both VRU treatments. And this is mainly because of establishment. So treatment 2 established very well and was able to mitigate the weed competition, and the others performed not as well in terms of weeds. So the main takeaways, the cover crop mix or treatment 2 had the best overall performance in terms of cover frequency and low weed percentages, and the wildflower mix and cover crop mix performed the best for floral frequency. And so the establishment and establishing all of this is really important to ensure low weed percentages and higher cover frequencies and higher floral frequencies, and then also creating seed mixes for the whole season in order to have that cover and floral frequency throughout the season. And then my recommendations depend on the land managers, what they want to mainly do. And so like if they want to do agricultural practices, I would recommend the cover crop mixes, which could be used for sheep grazing. And so that has become very popular recently and could be future research opportunities here at UF. And if they want more habitat conservation, I would recommend the wildflower mix, which performed well in the shade and non-shade.